Hello. So welcome to my live solve for Stat 110's 2017 final. Um, I think doing the practice finals is a really great way to study for the finals since there's just a lot of questions that you haven't seen before, and they're all very reminiscent of probably what the format of the actual final is going to be. Yeah, so as in the midterm review, I recommend that you guys go through and solve this final yourself before watching this video, um, because I just think it's a lot more meaningful when you can see the solution after you've had a try at it, got emotionally attached to the problem. So this is the first uh, video of the series. There's 8 problems on the final. Yeah, I actually went and dug up my own final from this year. So I'm going to like evaluate myself as I go as well. So yeah, let's get started. Okay, so here's the question. It's a Monty Hall variant. Okay, so Monty Hall is trying out a new version of his game. In this version, instead of there always being one car and two goats, the prizes behind the doors are generated independently. Okay, that seems pretty important. So we're not always going to, like, we could have 3 cars, we could have 3 goats. So the prizes behind each door are generated independently, with each door having a probability P of having a car and Q, which is 1 minus P of having a goat. In detail, there are 3 doors, behind each of which there is 1 prize, either a car or goat. For each door, there is a probability P that there is a car behind it, and Q equals 1 minus P that there is a goat independent of the other doors. Okay, so the contestant chooses a door. Monty, who knows the contents of each door. Okay, knowing the contents of each door seems important. He opens one of the 2 remaining doors, and in choosing which door to open, Monty will always reveal a goat if possible. So if there's like a car and a goat, he'll always choose a goat. If both of the remaining doors have the same kind of prize, Monty chooses randomly with equal probabilities. So if there's like a car and a car, he'll just choose one of the car doors to open. If there's a goat and a goat, he'll choose one of the goat doors to open. Okay, so after opening a door, Monty offers a contestant the option of switching to the other unopened door, which is the same in the usual case. Okay, so the contestant decides in advance to use the following strategy. First, choose door 1. Then after Monty opens the door, switch to the other unopened door. Okay, so let's do part A. Find the unconditional probability that the contestant will choose the car. So, okay. So we have like a few choices, like a few scenarios here. So we're either going to land in, like, we have like our 3 doors. And just like in the usual case, like we're going to go, we're gonna start off here, and then Monty will open a door, and then we'll like say Monty opens this door, then we'll switch here, and then we'll get that prize. He could have opened the other door as well. So we're going to win if there's like a car involved in the second 2 doors, because we're never going to get what's behind door 1. We're just going to focus our attention on what's behind door 2 and 3. And since all of this is independent, it just matters what's behind 2 and 3. We can compute that probability without doing anything. Okay, so we could either have like the CG case or GC case, like car, goat, goat, car. We could have goat, goat, or car, car. In the goat, goat case, we're going to see a goat, and then what's remaining is another goat. We're going to lose. In the car, car case, Monty opens a car door, and then we switch and we get another car. So we win here. And then in the CG, GC case, then we're going to, Monty is going to open the goat, and then we're going to get the car, and we must get the car. So we always win in this case. So this is up to computing the probability that we're either in this case or in this case. So this is going to, or I guess like you can also compute the complement of like getting this case. So let's do that. That's going to be 1 minus q squared. The problem, since they're both independent, it's each q. Then this is just the probability we're either in this case or this case. So converting that into just in terms of p, that's 1 minus p squared, which is going to be 1 minus p squared minus 2p plus 1, and that's going to be 2p minus p squared. So this is going to be our answer for A. Okay, so moving on to B. Monty now opens door 2, revealing a goat. Given this information, find the conditional probability that the contestant will get a car. So let's compute some, let's define some events. So okay, or I guess maybe let's think about the scenario first. So if we look at these scenarios that we just broke down, there's the CG, GC, GG, CC case. So we could have the CG case and we could have the GC case. Actually, in this case, we can't have the CG case because Monty opens door 2. So we can only have the GC case. We could also have the GG case, but in that case, we wouldn't win. We can't have the CC case because then Monty couldn't open to reveal goat. So these are our two cases. Let's just name this GC event, event goat behind 2, car behind 3, and then this is event goat behind both. And let's say we have let's call G2 the event Monty opens door 2 to a goat. And then let's have W the event we win. Okay, so what we're looking for is the probability that we win given goat 2 happened. So since there's a few different things that could happen, for example, that are just right here, I think I want to do law of total probability since there's a clear partition here. So let's write this out. Law of total probability. This is going to be law of total probability with extra conditioning because we have a goat 2 here. We just throw in goat 2 behind every term in the usual LOTP. So probability W given goat 2, or I'll go goat C comma goat 2 times probability goat C given goat 2 plus probability we win given goat 2 and probability goat 2. So we're never going to win in this case that we have 2 goat doors because we're always going to switch to another goat door. So this is actually going to equal 0. We don't have to do any work for that term. So looking at the first term, the probability that we win, given that there's a goat C and then Monty opens goat 2. So what's happening there is we have here and we have goat here, we have car here, Monty opens his goat and then we switch here. So we're always going to win. So this term here is just 1. So this is just going to be up to what this term is. So what is this term? So let's compute that. So we have that this is equal to probability goat C given G2. And let's just use the usual definition, the actual definition of conditional probability for this. So this is probability, we have goat C comma goat 2 over probability of goat 2. So when we have goat C, we're always going to have goat 2 in the scenario. So since goat 2 always happens when we have goat C, that means this is just equal to the probability of goat C, goat car, since the other one is kind of a subset of the events there. Okay, so we know that the probability of having a goat then a car in behind 2 and 3, that's going to be Q, which is the probability we have a goat behind door 2, and then P, which is the probability we have a car behind door 3. So the numerator is going to be QP. There's not going to be any factor of 2 since we're assigning directly that it's a goat behind door 2 and a car behind door 3, not there is a goat and a car in this mixture. So that's the numerator. The denominator is the probability that Monty reveals a goat. So there's a few ways this can happen. we could have, and the goat has to be behind door 2. So we can, Monty will reveal goat in this case, So goat car and goat goat. We couldn't do this because it wouldn't be revealed behind door 3. Not what we want. And in this case, since Monty opens the doors with even probability, it would be like 1/2 the probability that that happens. So we have, in this case, we'll have 1/2 times times this like first thingy, which is just going to be like q squared, 1/2 q squared, because that's probability q, goat, and then 1/2 probability we choose door 2. So this is choose door 2, and then this is goat, goat. And then we're going to have times PQ, which is just the probability, like this is car 3, and this is goat 2. And Monty will always choose the goat. So that's going to be our denominator. So we have, this is 1/2 q squared plus pq, and let's factor out a q. So that's going to be p over 1/2 q plus p. Let's multiply top and bottom by 2, so 2p q plus 2p. And then now let's finally just replace q with a p. So 2p, 1 minus p plus 2p. And then all in total, this is going to be p, 1 plus p. So this is going to be our final probability that we win, given the information that Monty will open the goat 2 door. Yeah, so that's it for problem 1 on the 2017 final. Hopefully this was helpful, and I'll catch you guys for problem 2.